Hooke's law is a really simple equation that gives us the amount of force needed to either compress or stretch a spring. And that formula is force equals K times X, where K is the spring constant. Now, each individual spring is going to have a slightly different spring constant, and that's really measuring how stiff a spring is. X is the distance we're going to either compress or stretch a spring. When we compress a spring, keep in mind, we're going to call that a negative distance. And when we stretch a spring, we're going to consider that positive. Let's look at an example of how this works. Consider the top spring. We're going to put that at a number line. That top spring, that's our equilibrium, so we're going to consider that X equals 0. Our bottom spring is when we stretch X 0.5 meters. We can use Hooke's law to find that spring constant for this spring. It's given us the force. We don't know our spring constant. That's what we want to find, but it's also given us our X value. We have stretched a spring 0.5 meters, so we've gone in the positive direction, which means we're going to put in a positive 0.5 for X. We can divide both sides by that 0.5, and we get the spring constant of 100. So anytime we want to find how much force is required to compress or stretch this particular spring, we can use this equation, 100 times X. Once again, this top spring is considered equilibrium. So this is when X equals 0. The bottom spring is when we compress that string 0.5 meters. Now, if you'll notice on our number line, we'd consider this negative, and that's why we set it up this way. We compress that string and we've gone in a negative direction for our distance. So we call X equals negative 0.5. And what we want to do is we want to find that work. Well, to find work, we're going to go ahead and take our force equation and we're going to integrate from A to B. A being our starting point and B is our ending point. So in this particular case, A, we start at equilibrium at 0. B is going to be where we end up. That's where we stop. And that's going to be the negative 0.5. We have our force, which is 100x times dx. We're going to go ahead and find this antiderivative, and then we're going to evaluate from 0 to negative 0.5. We get 50 times, and when we plug in negative 0.5, square it, and then we're going to subtract and plug in 0 for x. Well, this gives us 50 times 0.25, which would give us 12.5 joules, or we could also alternatively, we could change this into a fraction and say this is 25 over 2 joules. That's how much work is needed to compress this particular spring, 0.5 meters from its equilibrium position. Let's now consider a spring that's already stretched. Here's our equilibrium position at x equals 0. We're saying we have a spring that's already stretched 0.3 meters from its equilibrium. And now what we want to do is we want to go from 0.3 meters and we want to determine how much work is needed to take it an additional 0.4 meters. Well, if we're an additional 0.4 meters, what's our actual x value? We'd go ahead and add that 0.4 to the 0.3 and we get 0.7 meters. So we're going to plug that into our work equation. Our starting point is 0.3 meters. Our ending point is 0.7 meters. Our force equation is 100x, and then we have times dx. Well, we already know that this is 50x squared, and we're going to evaluate from 0.3 to 0.7. We have 50, and then we're going to plug in 0.7 squared, and then we're going to evaluate at 0.3 squared and subtract it out. We end up getting 20 joules. That's how much work it takes to take a spring that's already stretched 0.3 meters and stretch it an additional 0.4 meters.